Okay, let's start. There's a little bit to discuss logistically, and then we're going to dive into a little bit of a new topic. Hope you've all seen Lab 3 or project handout by now. There's the models have also been posted on Piazza as well as on the website, so a little bit more savvy could write their own just from the table. But anyway, it's up there. I wanted to alert you to sort of some of the timelines. So there's a few dates toward the end that are worth noting, and a little bit of a logistics. So what we're going to do this year is so we're going to have very quick kind of project presentations on May 2nd. That's not the time by which your project report is due. Again, this is the time by which you have to finish all your design and kind of be able to present the spec sheet together with the topology, right? And then you'll have, I think, till the 7th to turn in your project report. But on the 2nd, everyone will sort of stand up for 90 seconds and describe real quick what their topology looks like, what was the grand challenge they faced, as well as kind of show the specs that they achieved. And that means that the day before that, for us to collect kind of the who did what, we want you by sometime in the evening of May 1st, not midnight, because we still need some time to kind of aggregate everything, to post your one-slide summary that you're going to present, as well as the separate file containing your spec table, right? And based on that spec table, we're going to go and kind of nominate the best designs, and then these people we'll let them know. We'll have 3 minutes to talk a little bit more about how they really pushed the specs, right? So not much more material on that one slide, but you'll have a little bit more time to tell the class what's the secret sauce that you used to, do well. Okay, so that's just a little bit in terms of the project logistics. What we're going to do today is start with output stages. We're going to mix some bipolar work with CMOS. So far, we've mostly looked at CMOS op-amps, but I think it will be illustrative to kind of look back a little bit at what bipolars can do, especially because bipolars are very, very much superior in terms of the output drive and stage characteristics. So it's useful to kind of learn from that and then see how CMOS deteriorates that in certain topologies. When we talk about just the output stage, it's sort of a little bit different set of requirements than on all the gain stages that we were looking so far in an op-amp, where we were adding stages to kind of add gain, and the goal was to kind of boost the output impedance so your gain can be larger. Here, actually, it's quite the opposite. One of the first requirement is to sort of deliver specified power. To our load without distortion. So that means if you had a large gain in the driver stage before the output stage, that large gain was based on some large output impedance of the driver stage. And now you have to kind of do the transformation so you can still deliver that large signal to the output load, but the output load could be any resistance, right? Or any load. So in essence, you have a driver stage that already has developed a pretty large signal, and now you have to go into the output stage. If you look at this stage over here, our out is large. But this guy is loaded by an arbitrary RL. It could be 50 ohms, 100 ohms. It could be a kilo ohm, depending on the situation, right? And so the question is, how do you deliver the same large signal out, but for this arbitrary RL? And there's, depending on the topology, you'll see sort of a different efficiency. Also, if this is a sine wave, you would want this to be a sine wave as well. If it's a modulated signal, you would want to preserve those characteristics and do not include additional nonlinear terms to that expression. Nonlinear terms compared to a single tone would be kind of harmonics of that single tone, right? But in a more complex input signal, it could be something totally garbled. Okay. Under B, in order for this voltage Vi to be most faithfully copied to the output VO, in the situation where we have these different impedances, we want this driver to really act kind of as a voltage-controlled voltage source, meaning that its output impedance is very low. So it's really unaffected by RL. Remember that we've been sort of modeling amplifier stages as some gain and then some series or R out, right? And then you have RL here. So if this is very big, then this voltage is very small, right? So you want, in order to get as much out, you want to make this to be a very small resistance. So these stages have small R out. And then what you want to do is achieve A and B with smallest power. And largest bandwidth, right? You don't want this output stage to be sort of the bandwidth limiter to introduce a dominant pole in your amplifier. You also, we'll see later, you're drawing some power from the supply. So you don't want to have 1% of that power be delivered to the load. And so your total efficiency be 1% because you're burning 100 times more from the supply than you're delivering. So we're going to go through some topologies that sort of consecutively improve these numbers. Of course, simplicity and efficiency are not always kind of nicely aligned. So we'll see that the simplest topologies are actually not the best performing. So let's say a simplest output stage. Anybody have an idea what a simple output stage could be? Voltage follower, okay, good. So in bipolars, how do we call that? Okay, yeah, or emitter follower, right? Okay, so we'll have emitter follower, oops. I hate when it does this. Emitter follower, or in bipolars, and in CMOS. Yeah. Okay. So we're going to start with the emitter follower. So, so it could look something like this. You have the VI here, and then it's essentially this transistor, which is then loaded by a current source. So we can implement the current source as, let's say, Q2. We add a very small resistor, R2, just to stabilize the bias. Diodes are really always built as some form of a diode-connected bipolar, but it's simpler to draw them like this. Okay. So in this situation, we're going to load the output stage will be between minus VCC and VCC. This can be also asymmetric voltage if you want to really fine-tune things. And then you add RL to 0. Now, this will be kind of a DC current that the current source will provide. And then as the VI is changing, I'll be feeding some current here into the output. There will be the difference of the current from Q1 and the current I'm always pulling down from the current source. Okay. So in this case, both VI and VO are actually large signals. So even their small signal kind of amplitudes are going to be pretty large, because we would want to deliver as large a voltage to this output as possible. And that means, because our sort of small signal gain is kind of on the order of 1, that VI is also going to be very large. So we have to watch for that when we do the biasing. So the first thing is that VI is going to be VO plus this VBE1. Now notice I'm not writing it as a constant here. The reason is that I'm going to have this current in this Q1 go from 0 to some very large values. And for that span of currents, VBE is not going to be constant. It will still have some change in it that you have to take into account. So we're just going to use KT over Q log of IC1 over IS. Here I'm assuming that beta F is large, right? So IC. Okay. This is, of course, assuming that Q1 is in forward active region. And then we can go and write the KCL for the output node. Because we assume beta F is large, really IC1 is coming down here as well. So IC1 is going to be equal to IO plus IQ. And IO is VO over RL. So now we have that VI is VO plus KT over Q ln of VO over RL plus IQ over IS. Okay. This is a nonlinear equation, right? I don't have just this term over here so that I have a linear relationship between input and output. I have this term also that grows very slowly as VO increases, right? But depending on the value of RL, this term will be important or not. But in most practical applications, this is going to kind of be very small nonlinearity that you're adding to the whole system. And by tying negative feedback, we'll be able to linearize that as well somewhat. So if you take a look at this, we're going to take a look at a few regimes for the transfer function, depending what this RL really is and how important this term is overall. So let's go to the next one. What we're interested in is the VI versus Vout transfer function. So let's see what that looks like. Let's first find the point where Vout equals 0. So if Vout equals 0, then there is no current flowing through this, right? So 0 is here. And then Vin is going to be just VBE1 from 0. But IQ is going to flow straight through Q1. So then this VBE1 value is kind of very well defined by the current source value. So I'm going to say that this is now capital VBE1. This is equal to KT over Q ln IQ over IS1. And this is for Vout equals 0. Then from this point on, we can keep increasing. The slope is going to be very close to 1. Up until what point? Let me just delete this. What is the maximum output value that we can reach in this circuit? Assuming I can move the input any way I want. How big of a VCE can I have before I start going out of forward active region on this transistor? Yeah, or VC SAT, right? So this voltage can climb up, and correspondingly VI will have to come up all the way till this output hits VCC minus VC SAT. At that point, if I keep increasing VI, I'm going to forward bias this junction as well, right? So my max output will be VCC minus VCE1 SAT. And correspondingly, the input for that will be VCC minus VCE1 SAT, but plus VBE. VB1. At this point, VB1 is actually bigger than this VB1 over here, simply because we're also conducting the current, which is almost VCC over RL, right? Okay. So this was the voltage here. After this point, Q1 goes into saturation. So you're very sharply cut off over there. But over here, okay, I can't draw straight lines. Okay. So that's what happens on the positive side. On the negative side, anybody guess till where can I go? Let's take a look at this. How far can I go with VO on the negative side? You start dropping. When is this transistor going to change? It's forward active and it goes into saturation when? Assume that the voltage drop on this guy is very small. Okay. Yeah. So in other words, it will be kind of IQ plus R2 plus VC SAT. That would be the overall. But we're going to make R2 very small just to have some local negative feedback on biasing this one. So again, here we can go to minus VCC plus VC SAT 2. And then Q2 will be in saturation. Now, there was one condition under which you could do this. And that's the condition that RL is actually very large. Because notice, if VO starts going down, that means that some portion of IQ is actually now going from RL, right? Because IQ is the only one pulling down. And in the ultimate case, all of the current that goes from through RL is just IQ. Right? That's the lowest voltage that you can achieve on the output, right? So minus RL IQ. If that value is not equal to this value that I just said, then you actually end up prematurely cutting out the output. Right? So this curve is really for RL being large. But if RL is, or in other words, this curve is for RL that is greater than VCC minus VCE SAT2 over IQ. Right. This is my max output voltage I can get, and this, if it's all created by IQ, drop on RL, then RL has to be greater than this value for me to hit this limit. Right? If it's not, then I'll have some situation like this, where this value here, the max value I can hit, will be minus RL IQ. And so let's say we can say this is, for example, for RL equals RL2. RL2 will be smaller than VCC minus VCE SAT2 over IQ. So notice, when we hit that limit, transistor Q1 is off. Right? Because if you take a look at the previous picture, at that voltage, all IQ is flowing through VO. There's no current flowing through Q1, meaning our VI is so low that it basically cut off, is completely cut off. It's not supplying any current to IQ, so all IQ is going through RL. That's your best possible condition. Okay, so let's see, what are the implications of cutting off early like this? Does anybody see? If I provide RL that's very large, I have a nice symmetric transfer function. My VI can go from here all the way to here, and I'll be able to transfer that to these output range. But if I cut sooner, then I'll only be able to go from here to here and transfer linearly from here to here. Okay. So if you go and draw this function again, we have case 1 where you have this, and then another case where we can extend to be symmetric. If you go and put a sine wave here that has an amplitude that's larger than this, let's say we put something that looks like this, right? Then, okay, on this side. Then, in one case, we're going to get just clipping from the top. Oops. In one case, we're just going to get clipping on the top for this longer curve. So we're going to have a signal that looks like this. And then these regions are going to be clipped. So the sine wave is going to be clipped like this. Okay. However, in another case, the sine wave is going to be clipped over here as well. Right, so you're going to have a signal that goes all the way like this, but down severely clipped. So the output range that you really need to set is kind of symmetric to this. So this would be really the useful output range that you have. And that means that the input signal would have to look something like this to be able to satisfy this limit over here. Okay. Let's take a look at another view of this through a mechanism that we've sort of done way, way back in prehistory, maybe like first few classes, so maybe you don't remember, but we called it load line. When we looked at how you load an individual transistor and how that changes kind of the regions of operation in which it operates. So usually the way you look at it is by looking at IC, collector current versus collector emitter voltage. And if you look at the equations for this, for our Q1 device, what we have is that VCE1 is just VCC minus the output voltage. Right? And then VC1 would really be VCC minus, and then output voltage is really collector current minus IQ times RL. So now we have VCC plus IQ-RL minus IC-RL. So we have a relationship between these two axes, IC1 and VC1. And the slope here is minus RL. So if we assume that the quiescent operating point of this output, and you take a look here, it's for V0 equals, Vout equals 0. That's our sort of DC or steady state point. Then VCE will simply be VCC. Right? And for that value, Iout will be 0, so IQ will be the value of the collector current. And then for VCE equals 0, you have that IC is VCC over RL plus IQ, right? So here it will be VCC over RL plus IQ. This will be minus 1 over RL. Okay. Now on this one, we can add various transistor characteristics. So as we're changing VBE or Vin, we're going to have a bunch of transistor curves. Okay. Let me just draw it a little bit more BJT-like. And we can draw this one as going like straight through this as well. Okay, so on this one, we also can draw the maximum and minimum current VCEs that we can achieve. So we know that from the quiescent point, we can go up by VCC minus VC sat. So the largest value that we can get would be VCC minus, or 2 VCC minus VCE sat 1. Or sorry, in this case, it's the opposite, so it's 2. And on this line over here, this would be VCE sat 1. Okay. So as I start from my quiescent point, and I start increasing the output voltage, I'm going to start decreasing VCE up to the point where I hit VCC minus VC sat, right? So then VC is just VC sat. And then, so this is VO increasing. And then as I go down, VO is decreasing, I hit this point over here that doesn't necessarily have to be all the way down, depending on the value of the load resistance. Now, it's interesting to show sort of some of the extremes of the RL. If you have a very small RL, you're going to have a curve. Let me just maybe draw it in a different color. Maybe we're going to have a curve that looks like this. Okay. And what we said, remember on the previous picture, if we have RL that's very small, then even if the whole IQ goes through it, it will only be able to create RL times IQ of the V out, right? So it's going to be a relatively small voltage. So starting from the DC point, I'll only be able to make a small excursion for VO max. So let's say if this is our RL equals RL2, so this VO max 2 will be only this much. Okay. I was able, by going down this curve, to go down from IQ to completely cutting off this Q1 transistor, right? So my total maximum excursion in current is going to be IQ. So if I have a resistance that is very, very large, then my our load curve will look something like this. Okay. And in this case, I will hit this boundary over here. So I will be able to achieve this most negative voltage before Q1 turns off. And I won't need a lot of current through Q1 to be able to do that. This is just a different. So this will be my IO max. Let's call it 1. This is going to be RL equal to RL1. And in this case, my V output max 1 will be VCC minus VC sat 2. Okay. If I define the power, the average power, remember we're, for example, sending in a sine wave. Okay. So a sine wave with amplitude VO max has what power? If it's VO max delivered to load RL, what would be the power of that? Would have to do something with VO max, right? Squared and some RL and then something else. 1/2, right? Okay. So in other words, this you can say that this is VO max times IO max by 1/2. So if my objective is to deliver the most power to the output load, I can take a look at what this triangle is. And so if this edge is VO max and this edge is IO max, for example, in the RL1 case, this triangle will be, this area will be my average delivered power to the load. Okay. Similarly, in the red case, RL2 case, this area would be my average power delivered to the load. Now for blue, let me just draw it a little bit differently because I'm gonna redo it. I'm gonna draw it here. It doesn't really matter because these two triangles are similar. If I want to do the maximum one, where do I need to put my load curve? If I want to maximize this triangle area. Remember, by taking the curve and sort of rotating it around the pivot point, which is the quiescent point, I'm moving the slope, right? And if I go all the way to one side, I get a very small triangle. If I start moving all the way to the other side, I again get this very small triangle over here, right? So where's the best spot? Just geometrically. What would be the spot for this black line? What would be the area? Hmm? So it has to be some triangle around that line, right? So let's say in this case of the black one, your VO max will be up until this point, right? So it will be up until here, and your IO max will be IQ, right? Can you keep going? So that's obviously so that triangle would be kind of this whole area, right? Can you keep going? This point can move up to what point? How far on VCE can we go? To this one over here, right? 2 VCC minus VC sat. So I can keep lowering my resistance up until the point I hit this line. So my load curve rotates. So my load curve can rotate till the point that I hit this exact point. Okay. Notice, because I'm pivoting around IQ, in that case, my IO max is not changing. Right. Yep.
We can't really see like what lines you're pointing to when you say this line or this line.
Do you see this? There is a small dot. Okay. Okay, so I'll draw arrows then. So this green line over here is now optimized because it rotated around the quiescent point, and it was moving from this line to hit kind of this point over here, right? So now my overall area is this whole rectangle, sorry, triangle, right? So we can call this RL equals like RL3. So that will be 1/2 of VO max 3 times IO max 3. And that's VO max 3 is VCC minus VC sat. And IO max is IQ. Okay. Okay. So now we have sort of the best, this is really the maximum load power that you can deliver. Okay. If we take a look at how much supply power we draw, because this is a sine wave, it's sort of, in 1/2 it kind of draws power from the supply, and another half that guy's cut off, right? So you don't have any, so the average is sort of 0, right? So, or IQ is kind of the power that gets drawn all the time. But the supply is 2 VCC, because you have to provide minus VCC and VCC. So from total of 2 VCC, you're drawing IQ on average. Right? So if we can define sort of a coefficient of efficiency, it will be PL over P supply. And in this case, we had PL. So the maximum one we can get is PL max over P supply. And that is 1/2, and here we have VCC minus VCE sat times IQ over 2 VCC times IQ. So in this case, we can kill these two, and then what's left here is 1/4, 1 minus VC sat over VCC. Now, VCE sat is a lot smaller. It's like 0.2 volts compared to, in these cases, VCCs are around 5, 10 volts, 12 volts. So this item is like really negligible. So the best you can do in these topologies is basically to deliver about 25% of the overall power, supply power to the load. Another very important aspect in terms of preventing things blowing up in the lab and in life is to kind of look not only at power you deliver to the load, but what power is being absorbed or dissipated in the device that actually delivers the power. And if we take a look at sort of the waveforms, we can kind of figure out what the maximum for that is as well. I call it just PQ. You can call it also collector power, whatever. But it's going to be the product of the collector current and VCE. Right? And here we can see how that power changes. Now, we're not only interested in the average power that gets absorbed in the device, but sometimes you're interested as well in the instantaneous, because that could be something that, depending on what your thermal time constant is, that instantaneous power can actually blow up the device. So PQ1 will be IC times VCE. Right? So for IC, or let me start from VCE. We know from the load graph that we had previously, we start from VCC and then we're moving left and right depending how our V out goes as a sine wave, right? So we're going to go almost to 2 VCC. I'm going to neglect the VCE sat. So you can assume that this is like one period. Okay. And then the current changes, kind of has the opposite sign, but goes between IQ and 2IQ. When I'm supplying IQ to the load, I'm supplying also IQ to the source. So that's why at peak I have IQ. Okay. Not best at drawing sine waves, but you get a point. So now if you multiply the two, the maximum actually occurs at the steady state. So VCC times IQ is going to be the maximum point. Everywhere else, when it hits a 0, it's going to double that frequency. So the power will essentially, because it's like a sine squared, will have this type of shape. Okay. So now this is a little bit of a bummer, because notice that the largest amount of power that I'm burning on the device is when I'm doing nothing. Right? Notice it's this point of VC being VCC and IC being IQ is your quiescent point. So whenever the output voltage is 0, that's where you're burning most power in the device and not delivering to the load, right? So that's not a very good efficiency scheme. So in terms of the sort of just classification of output stages, we call these types of stages class A stages. They have bias when Vout equals 0. So there is the bias current flowing through both transistors in the output stage, even when V output equals 0. And that creates this large quiescent power. But it creates a pretty linear response. So you're trading off linearity for power efficiency. Okay. Another very useful view of looking at the device efficiency and the device power consumption is looking at again, sort of the VC over IC. But really look in this domain, looking at power curves versus the load line curves. So we said that, okay, our optimal load line would look something like this. That goes to 2 VCC minus VC sat, right? And this would be our RL equals RL3, right? Which is approximately VCC over IQ. Okay. If you start drawing the power lines, which are, remember, PL is 1/2 VO max times IO max. In this space, VCE versus IC, these are going to look like parabolas. Or we're going to draw a PQ. So PQ will be IC times VCE. And, oops. So they're going to look like this. What I'm drawing here is just for various PQ that I pick arbitrarily, each one of these lines means PQ, let's say 3, PQ1, 2, PQ1, constant, right? So if I just draw constant power lines that are products of IC, VCE, I'll get these different curves. And notice that on one of them, the way I'm going to touch this load line, this is the line on which I move, right? As my sinusoid moves like this, I'm going to be moving on this load line back and forth. This is VO, right? So notice that PQ1 is smaller than PQ2 is smaller than PQ3. So if I start from the quiescent point, anywhere I go on the load line, I'm going to go into the smaller power dissipation on the device. This is kind of just the same view of looking at things as looking at it in time domain for the sine wave and saying if I go from the quiescent point, anywhere I go, it's a smaller power dissipation than it was in the quiescent stage. Right? And then I start climbing back up towards it, I again get the same thing. Right? Another kind of useful thing to notice here is that you're always going to touch with this power hyperbola, the load line is always going to be the tangent on the power dissipation hyperbola. And then it's going to happen in the middle of your operating range. Okay. In looking at the emitter follower, you can sort of distinguish a few load scenarios for RL goes to infinity. Our PQ max, our load line would actually look something like this, right? And since you can only hit 2 VCC minus VC sat with IQ, then this would be kind of the power dissipation on the for the device itself. So the max you would be able to burn in the device would be 2 VCC minus VCE sat. Why is this important? Well, you want it not to melt or blow up, right? So there has to be some max power that will be able to sink. The worst case comes when in the lab you accidentally short the output, okay? And in that case, the load curve really becomes something like this, okay? And this is our sort of VCC. Now, there's really nothing practically that can, or in this case, if you just look at this curve, there's really nothing that limits this ICC, right? Okay, but in practice, IC max will be limited by the base current that the driver stage can supply, because the driver stage still needs to pump some current into the base of Q1. Plus, if the IC becomes very, very big and transistor very hot, you know that beta F kind of started having this type of profile with temperature. And also with very high collector currents, it starts degrading, right? So as you start increasing IC, beta is going to be going down. So you may get some self-limiting in that sense. Or IB will hit IB max, and this will be from the driver. However, here you're risking that, maybe it gets limited, maybe it doesn't before it blows up. So what people do normally, they add kind of like a protection circuit. So I'll just draw a little snippet here. So this will be I-base. And so the goal is to add some circuit here that will sense. We can do R here. And so this will be our R load. This is kind of the IQ pull down, so I'm not drawing that. So you want to sense how much current is coming through the collector 1, and then try to affect what amount of base current is supplied to Q1, right? So if this starts going up, this voltage, V sense, will be going up. And then you want to make sure that that will start sinking or decreasing I base, so that IC1 starts going down. Right? So what you do, you put essentially a transistor here in feedback. So now as V sense increases, VBE of this transistor, Q sense, increases. And then I start drawing more current here. So more of the I driver starts going this way and not into the base. Right? And then that's going to be OK, because I'm just going to pump that directly to the output, but it's not going to get amplified by the beta factor of this device. Okay. OK. That's, since I'm going to get cut off at 2:05, I'm not going to continue. For people who have time at 5, I'll also have a makeup for Wednesday lecture, and I'll kind of try to wrap up some more complex output stages like class A, B, class B. If you want to go out instead of coming to lecture, then you can always watch webcast. Okay.